measurement? Anybody want to volunteer? What's your measurement for that first one?
I got 154.7.
154.7, all right. Anybody else get something different? 154.80. Hold on, let's write this down. We're gonna forget. So we got 154.7, 154.80.
154.9.
Is it good to write like two uncertain numbers in between, like,
Sure.
you know, like
Yeah, like a range.
153, between 153 and 155.
Okay.
154.5.
154.5. All right, these are all sort of in the same range, right? Nobody got like 12 or something, or a million. I guess that's good. So let's talk about what the correct way to write this measurement is. What do you do first? What should we do first to determine this measurement?
Count how many ticks are between the two numbers on the other.
Yeah, count the ticks so you have a sense of what this scale is.
Right.
So in this scale, obviously the big ones are 10 because the numbers are 10 apart. And then we look at the little ticks and we say, okay, there's 1, 2, 3, 4, 5, 6, 7, 8, 9. So they're separated into 10. So that means each one of those little ticks is going to be a count of 1. So that means we can count this out as 150, 151, 152, 153, 154. So this measurement is definitely between 154 and 155 for sure, right? So we can write down 154. So is that it? Should it be 154 then?
No.
Why not?
Yeah, that's what I meant 154 with 500.
Okay, like that?
Yeah.
Okay, so are we done?
No.
No, why not?
Because we have one certain number.
That's right. We always add one more digit that we are uncertain,
Exactly.
plus or minus 1, plus or minus, within plus or minus 1 or plus or minus 2. So that last digit is uncertain because there are no more little ticks telling us exactly where it goes. So what did you call that next digit? What did you?
Well, it could range.
It could range. It just kind of depends on how you see it.
1 to, you know.
Right. Now it's true that it can range there, but you still want to make a good estimate of where you think that would be.
Right.
Now, this is a little different because you're way back there and this is way up here, so depending on your eyes, that may be the entire range. But if you're really looking closely at a measurement, you should be able to get at least within 2 or 3 of whatever you put down. So if you say this is 154.7, I think was the first one I heard, then what you're saying is, okay, I'm pretty sure this is between 6 and 8. It's 154.6 to 154.8. And so saying something like 154.1 is probably not a great measurement here because it's clearly not way down by the first tick there, right? So I would accept 0.7, 0.8, 0.9, just depending on how you saw that thing and especially as far away. But you want to be within a few. So those would all be okay, except what's wrong with this one here? This middle number. What's wrong with that?
You have the extra 0.
Yeah, the extra 0 is an extra degree of precision that we don't have on this instrument.
Right, because you're only allowed 1, right?
That's right, you're only allowed 1 uncertain digit. So that extra 0 would only be appropriate if there were 10 little dots right in here, and we could actually determine that last one. So you only get to pick 1 digit for your estimate. You don't get to add more on there. What we talked about also is what that means, what these different measurements mean. So in this case, we're saying that this measurement is between 154.6 and 154.8, a difference of 0.2, is the plus or minus 1 in that last digit. If we wrote this, we would be saying this is between 154.79 and 154.81. So this is a difference. We use a triangle, Greek letter delta for difference. So this is a difference of 0.2, and this is a difference of 0.02. which is a much, much smaller difference. Okay, so writing those two measurements are very different, and that's why we have to make sure to stop with whatever our measurement tool tells us to stop at. Okay. Any questions about that? Okay, I'll put the screen down. We'll solve this other one on the computer here so we can have it. If I can get back to my button, I guess I'll do it. All right, so we want to get 12 fluid ounces into cubic centimeters, knowing that 1 gallon is 3.8 liters, and a gallon is also 128 fluid ounces. So how'd you do this one? Somebody's going to tell me how you set it up before we talk about numbers.
Yeah, well, I converted the gallons to fluid ounces into the gallon.
Okay.
Then the gallon into the liters, then the liters into milliliters, and then then milliliters to
Cubic centimeters. Okay.
Cubic centimeters.
Okay, so let's put that plan down. So you saw fluid ounces here, and we need to get to cubic centimeters. So we have to get this there. So we're going to go. Whoops, that's a fancy F. Okay. Fluid ounces to gallons. How did you know to do that one first? Because it was there?
For me, I just
Yeah, remember that the main strategy here is, if we think about this problem overall, we're going from English units to metric units. So at some point, we're going to have to use this conversion to get us from English units to metric units, which means we have to get our ounces to gallons in order to get them to liters to get over to the other side. All right, so that's kind of the overall plan. You saw that in your head, so you knew to do that next. So that means we can go gallons to liters, and then liters to milliliters, and then milliliters to cubic centimeters. All right? And so we can figure out the conversions for each of these, but like we talked about last week, it can help keep everything straight if you set up the problem first and then put the numbers in, just so we don't get things on the wrong sides. So let's try that. We'll take 12 fluid ounces, and what do we want on top and what do we want on the bottom to do this conversion?
The gallon on the top.
Yeah, you want gallons on the top and fluid ounces on the bottom because we want to cancel the fluid ounces and end up with gallons. So that means we're going to put our 1 gallon up here and our 128 fluid ounces down here. Okay? So next, looking at units first. Liters on top and gallons on the bottom. And we can use our factor here. 3.8 liters, 1 gallon. All right, then we've got our liters on the bottom. Now this one isn't given because you're supposed to know this one, so what's the numbers that go here?
1,000 milliliters.
Yeah, 1 liter is 1,000 milliliters. And then we've got milliliters to cubic centimeters. What's the conversion there? 1 to 1, because they're the same measure, or the same amount of stuff, the same volume. So 1 cubic centimeter is 1 milliliter. To solve this problem then, you're going to take 12 divided by 128, multiplied by 3.8, multiplied by 1,000. So multiply by everything on top, divide by everything on the bottom. Whatever order you like to do that in is fine. And you end up with 356 cubic centimeters. That sound right? Anybody get something different? 0.25? Okay. Wait, like 0.25, 356.25. Okay. Yeah, so we'll leave it at there just because we started with like 2 or 3 figures, so we'll keep about there. But yeah, that's fine. Anybody get something else very different? What? You did? Let's see. Yeah. Oh, I think you just,
I think I multiplied.
I think you divided by 12.8. 0 and 1 by 10. Right, back by 10. Yeah. All right. Yeah.
356.25, would that be correct also, or?
Yeah, if you actually punch that all out, you said it comes to 356.25. So our rule in this class, we're not going to be strict about significant figures. We're just going to say, be reasonable. Whatever the problem is, yeah, 356 if you wanted to call this 360, if you want to call it 356.25. Like I said, there are rules about this, but for this class, any of that is fine. Yeah.
But cubic centimeters is a length, correct?
No, a centimeter is a length. A cubic centimeter is a cube with 1 centimeter on each side, which is a volume.
Oh, I was confused how you turned volume into length.
Yes, that would be difficult. That's what the little 3 means up on next to the centimeter, that it's a cubic centimeter. So it's a centimeter cube, which is a measure of volume, which is the same as a milliliter. All right, other questions about that? Okay, let's move on. So the quiz on Thursday will be these kinds of similar problems. All right, so our next part, which we're going to also do some in lab today, is dealing with matter and energy. We'll start with matter first. We'll get to energy next. How would you define matter?
Anything that has a mass.
Mass over volume is density. Anything that has what?
Well, just mass, but yeah.
Yeah, anything that has mass and occupies space, any stuff, anything. What kind of measurements do we use to measure matter? Usually. Yeah, grams. We usually measure matter by mass, but we can also measure matter by volume. So we can measure matter in terms of milliliters. And to remind us from last time, how do we relate mass and volume? What's that quantity called? Density. Yeah, density relates mass and volume. So that's what we're dealing with in terms of matter. All right, so I want to make a little tree here with some definitions that we're going to use to describe matter. We're going to split matter into 2 categories. So one over here, one over here. Matter is going to be split into pure substances and mixtures. How would you define those categories? Those aren't really crazy words, I don't think. Go ahead.
Pure substance is made up of only one component, and mixtures made up.
Okay, pure substances are only one component. Mixtures are more than one component. What do you think about that? Does it seem reasonable? Would you add anything to that? Probably about right. I'm not going to write any specific definitions here until we get in and actually look at some things. We're going to break these categories down a little bit further. We're going to talk about 2 types of mixtures. Heterogeneous mixtures and homogeneous mixtures. And we're going to talk about 2 types of pure substances. Elements and compounds. We're going to try to put some things into these categories. So let's look over on the right first. Let's look at mixtures. How would you, I don't know if you've heard these words before, but if you have, how would you, what would you say is the difference between a heterogeneous mixture and a homogeneous mixture?
Heterogeneous is made up of like different types of compounds, whereas homogeneous is like They all like the same types, they're like a class of compounds.
Okay, so closely related things would make a homogeneous mixture. Very different things would make a heterogeneous mixture.
Yeah.
Okay, kind of. Yeah, I think that's a reasonable start. Who'd like to add to that?
Homogeneous, they mix together smoothly and equally.
Okay.
Whereas heterogeneous, they mix, but they stay a little more separate.
Okay, they mix, but they stay a little bit more separate. Any other ideas? Any things you would add to that? Yeah, these mix. Now I'm going to preface this a little bit with these definitions are a little bit variable. In other words, depending on how you're looking at things, you can make an argument sometimes that something can fall in both categories. But given that, we'll talk about some general rules. So a homogeneous mixture is a mixture. It is not a pure substance. It is different things, but it looks the same throughout. So who can give me an example of a homogeneous mixture? Something that is made up of different things, but looks the same throughout its whole composition.
Water?
Water. Well, water, actually, we'll talk about that in a minute. Water actually falls into this other category because it's a pure substance. It's just, assuming we're talking about pure water. But you're right, it would be made out of some different elements. So we'll get to water in a minute. What else might you consider? Salt water. Okay, so that's a good example. What's the mixture of salt water? What different components are in salt water? Yeah, you've got the salt, the sodium chloride, you've got water. If you're talking about seawater, it could be all kinds of other stuff in there too. Why is that homogeneous though?
Because when you mix it up, it's equally dispersed throughout it, the salt and the water. You can't like pull them apart and separate them.
Sure. So has anybody ever seen salt water before? Is that a common? Okay. So it kind of looks the same throughout, right? Yeah. So that's a homogeneous mixture. Let's write that down as an example here. Salt water. Other kinds of things in water also make types of homogeneous mixtures. Things like coffee. An example of a homogeneous mixture. Coffee is made up of all kinds of stuff, right? It's got water, it's got caffeine, it's got flavor molecules, it's got color molecules. There's a bunch of stuff in there. Maybe you add milk to it or sugar, and there's that in there. But you can't say that the water is in this part of the cup and the caffeine is in this part of the cup. It all is the same throughout. So that's where we get this homogeneous, same throughout. So who wants to throw out another one? What? Another homogeneous mixture. Now that we're having a definition of that. I heard something. Kool-Aid? Yeah, okay. Blood? Is it with an I or a D? Yeah, there's a lot of stuff. Can anybody think of one that is not a liquid? A homogeneous mixture that's not a liquid? What? Oh, you just said, oh, okay. What might be a homogeneous mixture that is not a liquid? Concrete? Let's talk about concrete for a minute. What's concrete made out of? You know? Yeah, there's some sand, there's some rocks in it. What else is in it? Water, yeah. You put water in there and there's a chemical reaction that happens. Primarily concrete is rocks, or sand, like silica, rocks, that's bound together by cement, which is the binder that hooks it all together. So I think cement actually fits a little bit better in the heterogeneous category where it's visibly different because if you look at cement closely or concrete closely, you can see the little rocks. You get tiny little rocks and then stuff in between the rocks. But it also kind of gets to this question of what does it mean for something to be heterogeneous versus homogeneous, because it kind of depends on scale. If you just look down at some concrete, pretty much looks the same throughout, right? You might say, okay, that's a homogeneous mixture. But if you look at it really, really, then you start to see some of these differences. So that might in either spot. But I like, what would be another solid that you might think of more as a homogeneous mixture? Jello, sure.
Clay.
That's almost it. Everything. Jello, Kool-Aid, got all kinds of stuff. Yeah, clay would be another good example. Clay, Jello.
Sand or no?
Sand, sure, yeah. Again, kind of depends on your scale. If you get really
Yes, you-
in there, you might see some clumps of some types of, or here's an example. If you've been to a beach that has a lot of iron in it, you can see these kind of streaks of black in the sand. So in that case, it kind of looks heterogeneous because there's clearly iron-rich spots and then spots with less iron. So again, it kind of depends. So the book's official difference, so not a uniform composition. Yeah.
What is the invisible difference? We're going to get down the measuring in order to find out the difference.
Well, it's not so much it's a visible difference or not, it's how it's dispersed. How is it even dispersed throughout, where every little sample that you take is a good statistical representation of the whole, or are there kind of clumps of one thing in one spot and clumps of other things in other spots? So yes, we usually use our eyes to determine that, but in things like chemicals, that may not be the case. All right, so let's go back to our pure substances and define those, and then try to rank some or classify some different things. So if a mixture is some different things, then obviously a pure substance is just one kind of a thing. But I split these pure substances into two categories, elements and compounds. What would be the difference in those categories?
Would an element be like just a single element, whereas a compound is like a composition of like two elements or more?
Yes. So is that what you're going to say? Yeah. Yeah, so an element, if we want to be more specific, is only made of one type of atom. Next week we're going to talk about atomic structure, about what an atom is and what it's made out of. But for now we can just say that atoms are the smallest building blocks of matter, as shown in the periodic table. So each of those things, whether it's carbon or nitrogen or whatever, is a little thing called an atom. And if a substance is only made of one type of atom, so throughout the entire thing it's only carbon atoms, then we call that an element. That's just a sample of an element. It's a sample of pure carbon. So things will be named as such. So elements like what does carbon look like? It's actually a black powder. It's a black powder, like charcoal is mostly carbon.
Yeah, we look like that one left over.
What?
Our body is carbon.
Yeah, I mean most of all organic matter contains a lot of carbon. So if you get burned or if you break down over time, you end up being carbon. Other elements, metals like gold. And we're going to see this in lab in a little while, some different elements and what they look like. Now gold, I put this down here for a reason. If you have a gold ring, is that an element? Is that pure gold, probably? Probably not. Why? Yeah, why do you think that is? Partially it's because of its expense, but there's actually another reason. Yeah, pure gold is actually really too soft to make for good, durable jewelry that you can actually wear. Anybody know what pure gold is called, or how you identify pure gold? Measurement? It's a weird number, but it's 24 gold. Have you ever heard that that term? 24 karat gold refers to pure gold.
So that's not its purest form.
In its purest form. And so if you ever have something like a 24 karat gold coin, that is indeed pure gold. But you usually don't see 24 karat gold jewelry, rings, and that kind of thing because of its not durable nature. It'll get dense really easily, it'll bend easily, it just doesn't make for great jewelry. So instead, we get something like 14 karat gold or 10 karat gold, right? And that's been compounded with other elements, so that fits more into the mixture stage. So we might say something like 14 karat gold is a homogeneous mixture of gold and some other elements. So if those are elements, what are compounds? Combined atoms, right?
Sodium chloride.
Yeah. Two or more. But here's the key. Two or more atoms are chemically bound. They have a chemical relationship with each other that we'll talk about in a couple weeks called a bond, where their electrons interact in some way. Now we'll talk about what that means later, but for now, the way that you determine that is that compounds can only be separated by chemical means. Meaning that we have to do a reaction of some sort. We have to change the very nature of what that thing is to separate them. So if you have something like sodium chloride, it's a good example. What's sodium chloride? What we commonly call that? Salt, yeah. Salt, like from salt shaker. That's sodium chloride, made up of two elements, Na sodium and Cl chloride. All right. If we want to separate that into sodium and chlorine, the separate elements, first of all, we put in an enormous amount of energy, extremely difficult to do. And does anybody know what sodium by itself looks like? The element sodium?
Isn't it like white, like the actual sodium?
The actual sodium, yeah.
And you cannot even be touched by like humidity or water.
Right. It's actually a shiny metal, a shiny silver metal that is soft. You can cut it with a butter knife. And if it touches air, it reacts with the water and air right away, and it makes a white coating and sometimes can actually explode. So it's this shiny, soft metal. And what does chlorine look like in its element? Pure chlorine?
Gas.
It's a gas. It's a green, poisonous gas. So clearly very different from salt. And that's how you can really tell what compounds are. If they have to be broken up by something that completely changes the nature of that, then that's an evidence of a chemical change, and so that's a compound to start with. Now contrast that with something like salt water. So salt water is sodium chloride in water. How do you separate salt water? If I said I want to separate the salt from the water, what would you do? You could evaporate it. You could heat up the water or just leave it out, and after a while the water would become water vapor, and what would be left behind? Salt. But that's important, right? Because the salt that's left behind hasn't changed its chemical identity. It's still salt, it's still sodium chloride, whether it's in the solid state or whether it's mixed in with the water in the solution state. So, so that's how you know that this was a mixture and not a pure compound. That when the things were separated, they still maintained their chemical identity. All right, so let's try some. We're going to classify. I'm going to give you a few things to classify here. We'll see where you put it. Some of them will be pretty clear, some of them probably less clear. Let's say cheese sandwich. That's where you take cheese and you put it in between bread. You guys know? Okay. We'll then also look at cheese. Actually, we should be more specific. What's your favorite kind of cheese? Somebody? Swiss. All right. And then let's look at ice. And gasoline. So think about these four. I want everybody on your own to think about where you would put this, where you would categorize it. When you think you have an idea for all of them, and write it down so you remember what you say. When you think you've got all 4 of those, turn to somebody around you and see what that person said. And then if you have any that aren't the same, talk about the difference. I guess I'll be okay for today. I don't think it's too bad. But, yeah, there's something here in the car or something. So you gotta
I know. So I already mentioned separate. So you want to or more. Get into it.
There's some good arguments out there.
No,
All right, I'm going to stop you there for time's sake. So, what was your most controversial one?
Gasoline.
Cheese and gasoline. All right, so somebody who's discussing gasoline, what were you discussing? Give me your sides of your gasoline.
Because, I
debate.
mean, actual natural thing is raw from fossil fuels, and that it's a process because the actual fossil fuel itself is not like a car.
Right.
It also depends what type of gasoline is ethanol, but even that in itself is a mixture. So I was like, it's a compound. I'm like, not really. Well, I I don't know exactly the atomic structure or where it
Right.
comes from the periodic table because there's different types. If that were to be the case, then I could say it's a compound, but it's not because it is a mixture.
So you went with mixture. So was that the whole debate, or was somebody else going?
It was either homogeneous or a compound.
Or a compound. Okay. All right, good. Anybody else have? Do you have similar discussions about gasoline?
I put heterogeneous.
Okay.
Just visually, like not all the science stuff, like when you are at a gas
Not all the
station and
science
there's
stuff.
like gasoline on the ground, you
Yeah.
see like swirls of colors and stuff, and it's not very uniform. It's just,
Okay.
I feel like if you kept gasoline in the car, separate a little bit.
Okay. Other thoughts? All right. Well, I guess let's talk about gasoline then. So, can anybody? Here's a good way to tell if something's a mixture or a compound, by the way. If you can name a specific part of it that you know is in it, but is maybe not an element, is something else that's in it, then chances are a mixture, right? Because it's made up of something. So can anybody name something that is an ingredient in gasoline?
Ethanol.
Ethanol. Sometimes ethanol is added to gasoline. I think it always is, right? If you look at the pump, it says must contain at least 10% ethanol or something like that. So that's good. What else is in gasoline? Anybody need another? Gasoline comes from crude oil. It's distilled from crude oil. But the gasoline itself, we wouldn't say that contains crude oil. But anybody know of another compound? You ever see the numbers on the gas tank with the different pumps have different numbers? What is the number for octane? Octane is a molecule. It's a compound that makes up most of gasoline, and that number tells you how much octane is in there. So I think gasoline fits best in the mixture category, and I would say it's a homogeneous mixture. The fact that it looks different, especially when it's on the ground, there is absolutely explanation for that. One, what causes that swirling? If you see gas or oil on the ground, why does it look all colorful and swirly? You know?
Well, it's two different things of light that hits. It shines. I mean, all oils and everything it's shiny, but also the temperature of the concrete or the floor.
Yeah, that can all affect it. The main part is that gasoline and oil is actually less dense than water. We talked a little bit about density. So what's really happening is usually you see that. It's a little bit of oil or gas that's on the ground that's actually on top of a puddle. Mostly water with a little bit of gas or oil on top. And that thin layer, the difference in the two and how the two materials refract light into its spectrum, and so that's how you kind of see that rainbow effect. If you see other weird stuff on the ground, it's probably just dirt. And if you legitimately see like a puddle of gasoline, you should probably tell somebody.
Right.
This is not really good. Hopefully it's just some oil that's come out of somebody's car or something and not like a pool of gasoline. So the other controversial one was the cheese, the Swiss cheese. All right. What were some of the things you thought about Swiss cheese? Start us off.
Homogeneous.
Why homogeneous?
It looks, Swiss cheese is just, it looks the same throughout.
It's the same throughout. Yeah, uniform throughout.
Jello.
Okay. What? Anybody else want to add to that, or do you think something different?
Well, I think because it's just white, you can't really tell the different parts of it. You have to see the dairy portion.
Right. So that's what makes it homogeneous, right? Is that you can't really tell where one thing starts and ends. If you were to really look at just a tiny little bit of it, like under a microscope, then you might see pretty clear different domains, right? When we discuss things, we usually talk about them on whatever scale we're using it. So if we're talking about cheese that we're going to eat, then yes, I would say probably a homogeneous mixture because it looks kind of this out. If we're looking at cheese nanoparticles or something, then under a microscope, then maybe we have a different answer. But I would call this also a homogeneous mixture. What about the cheese sandwich? Heterogeneous mixture. That's pretty clear, right? There's clearly bread parts and cheese parts, and then it's not uniform throughout. And what about ice?
Compound.
Why is it a compound?
Because it's just, it changed shape, but the actual atomic structure is.
Yeah, ice is water, right?
Okay.
That is a compound. Whoops. And how do we know it's a compound? How do we know that it's not, that if we, okay, we know it's water, we know it's H2O. How can we see that as a compound? How do we know that's a compound?
Because if you break it up, you get two elements.
Right. The only way you can break it up is into two elements, hydrogen and oxygen, which we know are very different from water, and you have to use chemical means to break those apart. There's no physical, like, heating or something that you can do to break hydrogen and oxygen apart in water. All right. Good. So you think you have an idea of this? There's a lot of practice problems in the book. So through and see a bunch of these examples and talk about them. Okay. The last part that we need to talk about then, looking at matter. Can do this. I guess two more things. So states of matter. You could probably tell me the states of matter, right?
Gas,
Solid,
and
liquid. And I know you've learned that before. We're going to be a little bit more careful with our definitions now. Because if you think about this, you probably all have a good sense of what these words mean, right? But if I asked you to define a liquid for somebody who had no idea what that was, could you do it without giving an example? What is a liquid?
it flows.
That's a property of a liquid, but what is it?
It takes the shape of any object. I mean.
Yeah,
right?
yeah. So there we go. So we're going to define it as some type of matter that does something that makes it very different from other types of matter. So we're going to call solid. We'll start with solid because I wrote down first. We're going to say that a solid with a defined shape and volume. All right. A definite shape and a definite volume. If you have a solid, doesn't matter do with this. It keeps its shape, keeps its volume. Right? I can't compress it really. Just fine volume. So then a liquid is going to be matter with a defined volume that takes the shape of its container. So if I have 500 milliliters of water, that's always 500 milliliters of water no matter what I put it in. I can't compress that water to a smaller volume. I can't expand it to a larger volume. The volume always stays the same. But if I have that liquid in the speaker, it's going to take the shape of the speaker. If I pour that water on the table, it's going to take the shape of the table. If I pour that water in a long skinny tube, it's going to have a long skinny tube. So its shape is not fixed. So then what do you think gas definition is going to be? If we're thinking in terms of volume and filling a container, what does a gas do that's different from a liquid? Right. It has no shape or volume of its own. So take the volume and the shape have a defined mass. They're matter, they have a defined mass. But when you put a gas in this container, the gas fills the container. It doesn't matter how little you put in there. You can have a vacuum in here, you can have a little bit of gas in here, you can have a lot of gas in here under pressure. This is a defined volume that that gas will take. You put that in a different container, it'll change its volume as well as its shape. So that's how we separate these more technically. We can also talk a little bit about what's actually going on with the molecule atoms themselves. So what's, how would you describe the arrangement of particles in these three? How does that differ as you go from solid to gas? What changes with how the particles are arranged inside of it? What?
How close they are?
Okay, which ones have the closest? Solid, and then liquid, and then gas. What about the motion? Well, there's always some molecular motion. What about the position of the atoms?
It doesn't position it vibrates.
Yeah, in a solid, the atoms don't actually change. You're right, they still have motion with them, but they don't change where they are. What about a liquid? Yeah, so the particles are closer together in a movement, but they're still having random motion throughout. And then in a gas, the particles are very far apart and have random motion and are not really associated with each other. All right, good. So I know you know these definitions. I mean, you know what these things are, so this just gives us some more proper definitions. And then finally, we're going to talk about changes. And we mentioned this a little bit because you can't really talk about the other stuff without talking about this. And you'll get to practice this a little bit in lab today too. Physical versus chemical changes. We looked at this a little bit earlier to remind us, how do you differentiate between these two? If you think about a physical change versus a chemical change, how do you define what separates those? Heat.
It changes its chemistry of any type of element, I think, or not element, but compounds. When it's heated, it changes its atomic structure, I think.
It could. Some things could. But if you heat water, does it stop becoming water?
That's true. Yeah, you're right. I guess it depends on the outside force.
Yeah, it kind of depends on what's happened, what the heat is doing. So I would say heat could be applied in either of these situations. Heat can cause physical changes and chemical changes. What would you think?
I would say physical is a visual change. Maybe.
A visual change, so you can see it?
Yeah. Like
What's a chemical change then?
something like you can't see without an instrument.
Okay, maybe. That will sometimes apply, yeah. We want to add to that?
The physical change is a structural change in it. So like water going from a gas to a solid to a liquid, it's changing the shape, it's changing the structure of it, but it's not creating anything new. Chemical change has to create something new or break something apart.
Yeah, I think that's the key here is the change, creating something new, changing the very nature of what's happening. So I would say a chemical change forms new substances. Right. A physical change changes the state, or not always the state, but like you said, has to do with its appearance. So size, shape, other things about its. But crucially, not its identity, not what it is. So a physical change could be something as simple as a breakage. Like if I took this ruler and broke it in half, that would be a physical change. It's changed the way it's looked, it's changed what it is. But I haven't changed the material inside that ruler. I'm not actually going to do that.
So you used salt water as an example earlier. So if you took salt water and you evaporated the water, would that be a chemical change because you're taking the water away from the salt and breaking it apart, or is that just a physical change?
I think in that case we call that a physical change because you still have water, you still have salt. They were in solution together, now they're separate. But you haven't changed the identity. You didn't make anything new, you haven't changed the identity. Now some people would argue with me. When we get into solutions later, we'll talk about that because when salt dissolves in water, the sodium and chloride ions separate from each other and water. Well, that's a chemical process that kind of really inside the water. So there's some chemistry to that, but traditionally we consider a solution to be a mixture and that to be a physical change.
Because the molecules are still.
The molecules are still intact.
Water molecules and salt.
Right. So what can be an example of a chemical change, of something that you have seen or done? It doesn't have to be in a lab also, remember. There's chemical changes all over the place. What chemical changes happened in your car when you came here today? Or your helicopter?
Corrosion?
Corrosion? Sure. How do you know that's a chemical change?
I used an aircraft for it.
Okay.
Yeah.
Aren't aircrafts made out of aluminum? Isn't that,
No, but
they
it's
don't-
metal, it corrodes as well, so
Oh, okay.
we studied it as considered chemical change because
Yeah.
The actual metal the structure is actually changing.
It changes completely, right? So in an aluminum case, you go from aluminum to aluminum oxide. What about in a car? Do you know what that corrosion process is?
Oh, well, like when gas burns, it turns into like when your fuel burns, like power your engine.
Yeah, so that's another chemical change. How do you know that's a chemical change?
Because it produces energy.
It produces energy. That's always a good,
Well, it doesn't change like the
Marker.
state. It like reaction, destroys the chemical.
that's right. So you've completely changed the identity of the chemical. You had gasoline, which is octane and ethanol and the other stuff we talked about. And then what do you have after the engine?
Yes.
You have carbon dioxide, you have water, you have all the other byproducts of combustion. So back to the rust. What rusts in your car? What's the element that's changing mostly? Oxygen is coming in to react with it. What is your car mostly made of?
Depends on the car, but yeah.
In the car.
Yeah.
Most cars are iron, are mostly steel iron, unless you've got a plastic car. But even that, the frame and everything is probably still iron. But yeah, so iron reacts with oxygen from the air to form iron oxide, which is rust. And rust has very different properties from metal, right, from steel. It's a different color. So when we look for things like color changes, we look for things like changes in properties. Metal hammer, what happens? If you took a hammer to the side of your door, what would it do? It would dent, right? It would bend in, and you could bend it back. If you a hammer to a big piece of rust, what would happen? It would break and shatter. Really different properties there. Good indication that a chemical has occurred. Examples of chemical changes. For example,
Ice.
water to ice, yeah. Right? Water freezes, you still have water, it's just in a different form. Now it's becoming ice. What about cutting paper into confetti? Is that a physical change or a chemical change? Why?
It's still paper regardless, just.
Yeah, it's still paper, right? You don't change the identity of it. What about let's see. I think we're not like one.
Wood.
Yeah, we'll see some examples in the lab. Go ahead.
Would, using like the color dye and icing do a physical change? Or does it have to be physical change?
Question, ever hear that? Icing, right, like on cake? You put some food coloring in the icing so that you have nicely colored cupcakes. Is that a physical change or a chemical change? What do you think? You said chemical, why? Okay.
Wouldn't it be the same for confetti if the confetti was turned into pink? So be physical, right?
Yeah,
It's still paper.
so you're changing. You're going to go physical?
Yeah.
Okay, you're going to say anything. Who else said physical? I heard physical. Okay, why? Okay, so you haven't changed the chemical nature of anything? Yeah, I think that's what I do. So you've got your icing, you've got your color molecules. You're dispersing the molecules throughout the icing, but you're really changing the identity of that. Now, if you took some pink food coloring and you put it in your icing, and you stirred it around in your white icing, and you stirred it around and it black and started smoking, that would probably be a physical change, right? Or a chemical change, and probably you used the wrong thing. Also, you should not eat that cake. But one time I tried to dust powdered sugar on this chocolate I made, except I was in someone else's house, I didn't know where their stuff is, and I saw something that kind of looked like powdered sugar. It was baking soda. That was not good. Yeah. But speaking of cooking, what's an example, so you're baking your cake, what's an example of a chemical change that could happen in baking? The yeast that makes the bread rise? Yeah, so that's...
Sorry, right?
Yeah, I did, but that's fine. That's good too. Maybe it's a yeast cake. It's a donut, you know.
The whole thing is actually it's a chemical process in itself. Anything that you not considered.
Yeah, but I think there are chemical and physical processes involved. Like, for instance, you add sugar to your cake, right?
Yeah.
And the sugar is still sugar and hasn't really changed except for dispersed through the cake.
Correct.
However, something like the browning on the cake is a chemical change.
Right.
That's a reaction between the sugars and the proteins in the dough to make it delicious.
Well, the eggs is something that changes too.
Yep, and some of the things in the eggs are chemically changing. Some of them are physically changing. The proteins are stretching out in certain ways. So a lot of stuff going on in there. All right, now I'm hungry. Let's stop, and we'll meet back up in lab in 15 minutes. So please make sure you've got everything you need for lab, got the stuff printed out, all that. I'll see you up there.